All right, this video is to give a brief explanation as to why what we're doing in trig sub problems is legitimate mathematically. And so before watching this video, you should be very comfortable with the process of trig sub. You should have watched the two previous videos on this and completed most or all of the homework. So let's go quickly through this problem. So on this problem, we should know now that x should equal 3 sine theta. Dx is then 3 cosine theta d theta. We can come down to the bottom to get rid of the square root. So we're going to do the square root of 9 minus x squared. That's equal to the square root of 9 minus 9 sine squared theta. We can factor the 9 out. 1 minus sine squared is cosine squared. And the square root of 9 cosine squared is 3 cosine theta. And so we replace everything in the problem. So we get x squared to be 9 sine squared theta. The square root of 9 minus x squared gets replaced with 3 cosine theta. And dx gets replaced with 3 cosine theta d theta. The 1/9 comes out. The 3 on the bottom comes out as 1/3. The 3 at the end comes out as 3. The cosines cancel, and we get 1 over sine squared theta d theta. The 3's on the outside cancel. We rewrite 1 over sine squared as cosecant squared. The antiderivative of cosecant squared is negative cotangent theta. So we get negative 1/9 cotangent theta plus c. And now we draw a triangle. So we get x is 3 sine theta. We solve for sine theta and get sine theta as x over 3. We draw an angle in the first quadrant. And we have theta here. We label the opposite side, or the y side, as x. The adjacent side, the hypotenuse or the r side, as 3. We use the Pythagorean theorem to figure out that the adjacent side, or the x side, is the square root of 9 minus x squared. Cotangent is x over y, or opposite over adjacent. So we get negative 1/9 times the square root of 9 minus x squared over x plus c. We can simplify a little bit by making this negative square root of 9 minus x squared over 9x plus c. Okay, so that's a relatively simple trig sub problem. I want to talk about several places where some of what we're doing is questionably legitimate. And so when we look, first of all, at x equals 3 sine theta, that's questionable because sine theta is very restrictive. Sine is always between 1 and negative 1, which means we're restricting x here. So there's a restriction on x that is a little bit unclear as to why that's okay. Another spot is when we go from the square root of 9 cosine squared theta to 3 cosine theta. We talked in the intro video on trig sub about how that really should be the absolute value. And so should this be an absolute value, or why is it okay to do that? And then here, is this too restrictive on x? And then another thing is, why down here is this quadrant 1? How do we know that theta is in quadrant 1? And then the last thing, which didn't occur in this problem, is if we had had an x or a theta that was not part of a trig function. So like in this step, if we had had, say, negative 1/9 cotangent theta plus 6 theta plus c, how come we can do inverse sine of x over 3 to replace theta there? And so we would have, had the same thing here. So negative square root 9 minus x squared over 9x. but why is this part okay? So is inverse sine too restrictive? Remember that from trig, there's a domain restriction on inverse sine, and there may not be on theta. And so let's talk about those assumptions and why what we're doing is okay on each of these steps. But if you back up and kind of look at the problem, pretty much that's everything that is new as part of this. So we need to justify what we're doing. We're not going to go through in detail on secant or tangent, but similar justifications can be made for those. So one thing that we've not stated prior till now is when we're doing the trig substitution, when we're doing sine, we're making the assumption that theta is between negative pi over 2 and pi over 2. There are a few reasons we do that. It doesn't affect the mechanics of the problem, which is why we've not mentioned it until now, but it does affect several things. So one thing is back over here where we've got x equals 3 sine theta. Not only might that be too restrictive, but another weird thing about sine is it's periodic, where it repeats all the time, and that's not probably true of the function that we're looking at in a trig sub problem. Well, negative pi over 2 to pi over 2, if we look at the graph of sine theta, that would get us the entire range of sine exactly once. And so it covers everything from negative 1 to 1, which is the entire range of sine, and it hits every one of those values one time, which fixes kind of the periodic problem. Another thing is that this restriction really indicates that x has to be between negative 3 and 3, because sine is at most 1 and at least negative 1. That means 3 times sine theta is between negative 3 and positive 3. Normally, that assumption is not allowed, but when we're talking about a square root, it's understood that the value under the square root needs to be non-negative. So 9 minus x squared already has to be positive. If we think about what that would make, or what would make that true, values between negative 3 and 3 are the exact values that the square root would restrict us to anyway. And so this is not too restrictive. It's okay because it's the same restriction that the square root places on the variable anyway. If you look at tangent, tangent's range is negative infinity to infinity. When we do tangent, that's when we have problems where there's addition. There would be no restriction on x there. There is a restriction when we do secant, and it matches the square root restriction anyway. So we're okay on that first assumption. On the second part, when we're talking about should this be absolute value here, so we said on the video talking about square roots, the intro one to trig sub, that you needed really to have an absolute value when you take the square root of a variable like that. And so it turns out that's not true because of this negative pi over 2 to pi over 2 assumption. So if we think about angles between negative pi over 2 and pi over 2, they're angles in the first, don't want that to be a straight line, they're in angles in the first and fourth quadrant. So they're here or here. Cosine is always positive there because x is always positive there. If you get a value that's on the y-axis, cosine is 0, but that's okay. And so the absolute value is okay because we know that cosine is not negative on the restriction that we're using for theta. Okay, if we look at inverse sine here, so I think the last one I listed, but the next one I want to talk about, inverse sine's domain restriction is the same as negative pi over 2 to pi over 2, which means this is also okay. And that's why in the previous video we said that when you do an inverse trig function, you typically use the trig function that we originally chose. That's because then the domain restriction matches the domain restriction of the inverse trig function, or of the trig function that you chose. Okay, last thing we want to talk about is why is this okay for it to be in quadrant 1? So it gets us the right answers is basically the answer to that question. It is possible that the diagram really looks like this because it could be between negative pi over 2 and 0. If that's the case, then when we label the diagram, we use this x over 3 So x is here, 3 is here. This side is the square root of 9 minus x squared. There's no change. We don't need a negative on this x because even though there's a negative y value, in this diagram, x itself would be negative. That means that when we start reading things from the diagram, all of the answers we would get are the same as the answers we get from the diagram we used. So it's okay to assume that we're in a quadrant 1 angle, even though it might be a quadrant 4 angle in this problem, because we end up getting the same answers. What we use the diagram for, that's enough. We could set up the same type of theory for substitutions involving tangent or secant. We're not going to spend the time to do that. If you want to talk about that, I'm happy to talk about it with you. When we're doing the problems, most of this theory isn't relevant when we're actually doing the problems themselves. It is important to kind of keep it in mind as we go, but it doesn't affect the mechanics of the problems. All right, thanks for watching this video.